Good evening, everyone. I'm Dr. Sarika Chauhan, Chair of the Program Committee at EdTech Society and Associate Professor at Atlas Skilltech University. It is my pleasure to welcome you all to Masterclass 24, Designing Agent-Based Computational Model to Support Epistemically Agentive Learning. Before we begin, let me tell you a bit about who we are. The EdTech Society is a professional association started in India by individuals who are committed to improve instruction and learning through the use of educational technologies. EdTech Society members are researchers, developers, and practitioners in the field of educational technology. Joining EdTech Society offers numerous benefits like networking and collaborations with experts in educational technology, opportunities for professional growth, affiliation with international associations, awards, scholarships, and internship programs, reduced registration fees for annual conferences and faculty development programs, winter and summer schools, access to key resources and best practices in educational technology. We conduct various events like Masterclass, Industry Talk, InFocus Interview, Perspective, a panel discussion, T4E Conference, and many more. The International Conference on Technology for Education, T4E 2024, organized by EdTech Society India and hosted by IIT Gandhinagar, will be held in IIT Gandhinagar from 6th to 8th December 2024. So join us and unlock a world of opportunities in educational technology. For more details, you can visit our website etsociety.org. Now, let me introduce our esteemed speaker for today's masterclass. Dr. Sugat Dabolkar is a learning scientist who works in the field of science education. Dr. Sugat is currently a research assistant professor in the Department of Education at Tufts University. Before joining Tufts, Sugat worked as a postdoctoral associate at Rutgers University and as a distinguished research fellow at Northwestern University. Sugat completed PhD in learning sciences from Northwestern University. Over the past several years, Dr. Sugat has designed and co-designed several computational agent-based models and curricula, many of which have been used in high schools in the US as well as in India. He has presented his work at several highly prestigious international conferences and authored several peer-reviewed journal publications. Before starting his PhD in learning sciences, Dr. Sugat was first a computational biology researcher and then a science content developer for a multinational organization in India. So, on behalf of EdTech Society, I extend a warm welcome to our esteemed speaker, Dr. Subodh Dabolkar. We are delighted to have you here today. Before I hand over this session to the expert, there is an announcement for the participants. You can post your queries using the comment section on the YouTube, and the answers will be given towards the end of the session. So now I request Dr. Sugat to begin the session. Thank you. Over to you, Dr. Sugat.
Yes, thank you. Thank you, Dr. Sarika. Thank you for the kind introduction. And let me share my screen and start the presentation. So once I share my screen, it's unlikely that I'll be able to see the video. So I'm assuming that you will be able to hear me. Those who have joined the live session, welcome. Excited to have you here live. And so I will try to have some interactions and we'll see how it goes. And if it's turning out to be difficult, then we can switch to a different mode. Okay. So let me share my screen and start. Okay, good. So I'll be talking to you about designing agent-based computation models to support epistemically agentive learning. And I'll quickly tell you a little bit about how I got where I am So I did my school education and junior college education in Satara in a Marathi medium school. I did my bachelor's in Pune. Then I went to Bangalore to study biological sciences. Um, and I did like detour. I moved to Jamshedpur, studied at XLR. I did MBA in human resource management and organizational behavior. That was my interest during my MBA. I moved on to doing research in learning sciences. So I did PhD at Northwestern University. Um, I did a postdoc at Rutgers University in New Brunswick, and currently I'm a research assistant professor at Boston in Tufts University. And I see myself as a teacher, educator, and researcher. So the first thing I'm going to try is uh, could you please write your name and your identity that is sort of central to your work as a teacher, as an educator, as a researcher, as a computer scientist, whatever. So your name and your uh, identity. If you put that in chat, that would be great. I'm going to be looking at the chat.
Dr. Sugat,
Yes.
can you just reshare your screen? We can't see your PPT presentation.
Oh, it. Did you see it earlier or when I was talking or no?
No, no, no.
It's still not visible?
No, no. Can you just reshare it, please?
Yes. Is it visible now?
Not yet.
Okay. This is surprising because we just tried it right before the.
You can just go to present and share screen.
Yes, yes, I'm doing that. Maybe I will try sharing entire screen and see if that is better. Yeah, I was
Yes,
just sharing a
yes,
window and yeah.
yes. If you
Okay, so
can
I was
just
just
put it on the
talking.
present.
Yeah, I
Yes,
was.
yes.
Yeah,
Perfectly. Yeah.
yeah, I was. Yeah. No, but now you will see everything in the background, but that's fine. So let
You
me
can
see
put
if
it on
anybody
a,
has.
you can,
Mm,
yeah,
That
put it on a
that's okay. That's
presentation mode.
okay.
Presentation mode.
No, I know. Yes, I know what you're
Thank you.
suggesting, but I'm trying to see if I can interact with the audience at all. If not, that is fine. We will just do the recording. Okay, so I don't think that is possible. So I'm just going to talk into the void and hoping that uh, people will be able to follow
Yes.
along. Okay, and if there is, so can you see my slides now?
Yes, yes. Please continue. Yeah.
Okay,
So
great.
just click on
Um,
hide that sharing this one, the hide.
y- yes,
Yes.
perfect,
Yeah.
perfect. Yeah, okay, great. So yeah, it's funny that most of the technology related talks start with some technology trouble. So that is common all across the world. Uh, anyway, so yeah, so I don't think we will be able to do any kind of interactive things during the session, but that's okay. I will talk for next 40-45 minutes, hoping that you are following along. Um, and then we will have some conversation, discussion, questions, etc., etc. Meanwhile, feel free to type your questions in chat, and the organizers will try to capture those questions and share them with me. Okay, great. So I'm going to be talking about co-designing agent-based computational models to support epistemically agentive learning. And there are a lot of complicated terms here, which I'm going to simplify during the lecture or whatever, during the talk. So first I will talk about design-based research, DBR, for educational work, educational research very quickly. And then I will move on to talking about agent-based models, epistemically agentive learning, and creating learning environment for supporting epistemically agentive learning. And we will talk about pedagogy, design, and co-design. So design-based research is a methodology that is mostly developed in the field of learning sciences, and it's now widely used in various other domains, other fields as well. And on this slide, on the right side, you see four quadrants. And on x-axis, on the horizontal axis, there's considerations for use. And on the vertical axis, there is quest for fundamental understanding. So the top left quadrant, which is no consideration of use or very little consideration for use, and quest for fundamental understanding is pure basic research, which is like quantum mechanics or understanding how different elements work or biological research, etc., etc. There is pure applied research, which is designing cars or making stuff that is technological innovations, etc. But design-based research falls in a quadrant called Pasteur's quadrant, which is highlighted at top right, which is user-inspired basic research. So it's a basic research that is meant to be used in complex real world settings. So it should have application. So it's basic and applied together. It is based on theories of learning and teaching. It involves data-driven analytical evaluation of learning materials and teaching practice. And the goal is to contribute to usable knowledge to foster learning in complex learning settings. So this is how I conduct my research, and I'm going to talk about some of my research in connection with using these agent-based models in classrooms. So what are agent-based models? Let's start there. And I'm going to go with Wikipedia definition. An agent-based model is a computational model for simulating the actions and interactions of autonomous agents, both individual or collective entities, such as organizations or groups. And these are created to understand the behavior of a system and what governs certain kind of outcomes that we observe in the system. And these models have applications in various fields, ranging from biology, epidemiology, business, etc., etc. And I'm going to show some of the agent-based models that I have designed and how those can be used in regular classrooms. And I have done this work with high school students, but I know that these models have been used at undergraduate settings and ranging various topics from biology to economics to computer science. So let's look at this example. And this is a video that I shot at a state park in the United States, where these are geese flying, and they have this interesting formation. And so the question is, how do birds form a flock? Is there a leader bird that directs all the birds, how to go, where everyone should be, how to move, etc., etc., or something different happens? And this question was taught by several people over decades. And in late 1980s, Reynolds proposed this idea that there's something happening at agent level. The birds, individual bird being an agent, follow simple rules related to three different things: alignment, cohesion, and separation. So alignment meaning whether I'm matching the direction of my neighbors. Cohesion is whether I'm moving towards the center. And separation meaning collision avoidance. Am I not colliding, or am I colliding with my neighbors, right? And so with these three simple rules, we can get various interesting patterns in flock formation. And so this is a NetLogo model, an agent-based model of flocking, where you can have these parameters associated with each individual bird, and then you can see various flocking patterns arise, and you can change various parameters and get different kind of patterns. Okay, so an important aspect here is these parameters that one can tweak and manipulate to investigate behavior of system, and we're going to talk about these parameters. Before we get into that, I also want to introduce the software which can be used to create such models. It's called NetLogo. It's a programming language and integrated development environment for agent-based modeling. It was designed with multiple audiences in mind, and this is very important because it can be used effectively for teaching children as well as scientists and professionals can use, even without programming background, use NetLogo to model different phenomena. And importantly, so NetLogo environment enables exploration of emergent phenomena. And so let's talk about what is emergence. So emergent systems are systems in which uncoordinated interactions between autonomous agents result in regular patterns at the system level. And these systems are ubiquitous. So for example, financial systems, so share market rising up, falling, etc., globally, locally, at various levels, various degrees, and colonies or networks of genes and proteins inside our cells. All these are examples of emergent systems. And so this emergent systems perspective has transformed fields of scientific research. For example, systems biology, complexity economics, natural and artificial intelligence, so neuroscience and AI, etc. Even like self-driven cars, and there are some interesting agent-based models that are being used in various forms in self-driven cars. Research in learning sciences over last 30-40 years has established that it is hard to learn about emergent systems. How does emergence arise through agent interactions, and what does it mean to study properties of such systems? So agent-based models have these computational representations, which I'm referring here as agent-based representations. They reduce perceptual limitations to learn about emergent phenomenon because they have these properties called restructuration properties, and we will talk a little bit about those properties later. So I in my PhD work, I have coined this term, Emergent Systems Microworlds, to talk about specific kinds of agent-based models. So agent-based models that are designed as interactive computational microworlds. And this microworlds idea is from Pappert's theory of constructionism. So Samuel Papert, who has contributed a lot to develop to educational research over the last several decades. So the idea of microworlds comes from the theory of constructionism, and ESM is a computational microworld in which one can manipulate agent properties and behaviors to investigate emergent patterns. So what does this mean? For example, this is an ESM that I have designed with a teacher, and this is about a population of pocket mice which have two colors. So this mice live in a desert of Florida, and this desert has rocky regions and sandy regions, and there are predators that eat these mice. So the mice that live in sandy region, if they have light fur, then they can hide well. The mice in the rocky region, if they have dark fur, they hide well. And so over time, populations of these mice have changed such that the dark mice are found in rocky regions, and light furred mice are found in sandy regions. And so students can use this model, change settings, and sort of simulate conditions and understand how populations change over time. And so this is to study natural selection as one of the important concepts in evolutionary biology in high school. So in my dissertation work, I have established 7 core design principles of Emergent Systems Microworld. The first one being we can visualize agent properties and interactions. So here, predation is an interaction, reproduction is an interaction, fur color is a property, right? So we can observe that there are some mice which are dark, there are some mice which are light. We can visualize system level emergent patterns. So we can see right now on the right side where there is dark background, there are predominantly dark mice. On the left side, we see there are predominantly light colored mice. We can manipulate agent properties and interactions. So we can make some changes. We can change, for example, chance of predation as a parameter, and that means the predatory pressure is higher, so there is more chance of being eaten. There are a lot of predators, right? So we can change that. We can track system level changes. So there is visual tracking, but there are some numbers that you can see. So there is data in terms of genotypes and phenotypes of these mice that you can use to track. The coding, so we haven't talked much about the coding, but the code is easily accessible and you can read the code. And the coding is agent based. What that means is the code controls interactions between agents and not what is happening in the population. The code is controlling what individual mice are doing, but not how population should change. How population changes is because of emergence. So, 2 important validity things that are also important. One is micro level validity, so validity of agent rules. So, the rules of inheritance, for example, if those are modeled properly. And second is macro level validity of emergent patterns. So, is it really happening that the dark colored mice are predominantly present in the dark regions and light colored mice are predominantly present in the light region? So these 7 ideas are core design features of ESMs. In the next part, I'll talk about using these ESMs for teaching and learning. And I have used them in various different settings in the US and in India with different teachers to learn and teach various different topics. Today's focus is epistemically agentive learning using ESMs. And so when we think about playing sports, right, we don't read how to play cricket or how to play badminton. We just take a bat and go on the ground or take a ball and go on the ground and start playing. When we think about music, there is some theory involved, some notation involved sometimes, but you also practice. But when it comes to science, we don't really do what scientists do. We learn in our classrooms what our teachers teach from textbook, which is mostly the ideas that scientists have established. Currently, those ideas we learn, but we don't learn the practice of science. But the new policies all over the world, including national education policy, is promoting shift in this direction. And next generation science standards in the United States have these list of practices, which are called science and engineering practices. And I think it's important to teach these practices to our students in engineering, in medicine, in so undergraduate programs, as well as in in schools, right? So what it means to ask interesting questions or define important engineering design problems, developing and using models, performing investigations, doing data analysis, doing mathematical and computational thinking, and we'll talk more about computational thinking, then constructing explanations, engaging in argument from evidence, right? So if I want to decide whether a specific bridge to be built or a specific flyover is to be built, what is the evidence that I have that it will reduce traffic load and so on? Or if I am proposing an idea that this mouse has a mutation and that mutation will spread in the population, how, what, on what basis I'm making that argument, etc. And then evaluating and communicating information is also very important. So this computational thinking part also has a different set of practices that are characterized by Weintraub and colleagues. And so combining all this in uh, in my work, I focus on how students can participate in these practices. So data practices, modeling and simulation practices, computational problem solving practices, and systems thinking practices. In epistemically agentive way. So what is epistemically agentive learning? So epistemic, and if you are in educational research, then you would have heard this. If not, don't worry about it so much, but it's an important idea. So it is about consumption, evaluation, and construction of knowledge. So we consume a lot of knowledge. We read from books, etc., etc. We listen to news. That is also some form of knowledge. Evaluation, right? So we get a lot of WhatsApp messages. There are some that we know that they're false. There are some that could be true. There are some that are really true. And construction of knowledge is basically what scientists do or professionals do when they are working in a cutting edge area where nobody in the world knows the answer, right? And they have to figure it out, and they do figure it out and contribute to the knowledge in the world. But I think students should be doing all these three things. And so epistemically agentive learning involves taking an active role in consumption, evaluation, and production or construction of knowledge. So how can we use these agent-based computation models designed as ESMs to support this? And so my research sort of has identified 4 stages in which we can do that. So this is the pedagogy of using ESMs. First, students should do unstructured exploration of the model system. They should just play around with it. And the model of mice that I showed, I would give it to students and ask them, okay, here is a model of a population of mice in a desert, and there are some buttons, etc., etc. See what you observe. Do you see anything interesting? And they share their ideas. The next step is important. In the next step, we do systematic investigations by designing experiments and analyzing data. So students ask questions and form hypotheses and collect data, analyze that data. And then third part is where they present their findings to build shared understanding in the classroom. And then we would have discussions to decide which claims are established and which are unanswered questions. And then we would do more explorations and so on. So this is an iterative sort of cycle. And so in this particular example, first I would give this model for students to play with and make observations. There is some thing about homozygous, heterozygous, genotype, phenotype, and these are some advanced ideas in genetics. And students who can use books or whatever. So these are not like exam, right? So they are playing around. They have some information about some of these concepts. They can check whether their understanding is correct or not, make some observations to begin with. But then I would ask them to have research questions. So if I introduce dark fur mutant in a light furred mice population, where the environment is dark, what will happen to the population after 300 generations, right? And so that could be a research question, and the hypothesis would be it would change in a particular way. An experiment would be that I would set the parameters values like this. I would conduct 10 trials. I will collect this data, then I will analyze that data and see whether this introduction of mutant is making any change or not. And I will conduct similar kind of experiment where I don't introduce the mutant and I make the comparison and see if there are statistical differences. Then the students would share their findings. So different student groups would conduct different investigations, and then they share those with each other and collectively learn um, about the system. And then we would have discussions about what did we learn about natural selection, what claims are really correct, what claims need more evidence, and do we have any new unanswered questions, etc. So we would do that. And I did this work with students and analyzed their participation. And the findings are that social properties of ESMs support students to build upon each other's idea, to even shape research practices. So how can we conduct research using ESMs and learn biology when the model is about biology? The cognitive properties of ESMs reduce perceptual limitation that are often encountered while learning about emergent systems. So if I start talking about uh, fur color of a mouse and then population changing over generations, on one hand I'm talking about single mice, and on other hand I'm talking about population, and that causes some kind of perceptual limitations which are dealt with when we have agent-based representations which allow visualization at micro and macro level. And affective properties of ESMs make learning of these complex ideas engaging and enjoyable. So how can we have such kind of units being used in various different schools, let's say in India? And this question has sort of been my design and research question, that how can we have these models in various different settings? So for that, we have come up with a framework and which we call CTSI, computational thinking and scientific inquiry. And so that involves asking questions, planning and carrying out investigations, developing and using models and simulations, collecting, analyzing and interpreting data, programming to create or modify computational processes, engaging in systems thinking, engaging in argument from evidence, constructing explanations, obtaining and evaluating and communicating information. So if we intentionally put these nine practices, or some of these nine practices in our different lessons, we are allowing students to engage deeply in epistemically agentive way. So if they're allowed to ask different kinds of research questions, they're expressing their agency, right, to decide their epistemic pursuits. And at every stages, if they're allowed to choose how they want to go about participating in that practice, rather than just telling them, okay, do this, do that, step one, step two, step three, you're done. So instead of that, we can use these models to allow students to decide how they want to conduct their experiments, how they want to modify the models, etc., etc. And then that would be an epistemically agentive learning. And to create such units with teachers, we conducted a workshop, a 3-day long workshop, and then a few teachers from 10 teachers from 5 different schools worked with us in different co-design teams to create units. And so those co-design meetings would involve creating new net logo models that teachers would use in their classrooms, and then how they would teach using those models. So pedagogy. So what would be the activities that students would do, and how teachers would support student participation, etc., etc. So we designed them, and we created these six co-designed units, which were used to taught 182 students, and now they're being used. So these are published uh, on an open source website, and students from all over the world are currently using these units. So Mendelian inheritance, free fall and the gravity, kidney reabsorption, um, coordinate geometry, and pendulum. So kinetic, so simple harmonic motion. So these are the units that we had, and so I will briefly, quickly tell you about one unit, and we will listen to a teacher talking about her experience of working in such co-design way. So this unit is about reabsorption in kidneys, and that we designed with a teacher whose name is Vidya Pillai, and Shraddha was an intern on this project, who is currently a very renowned science educator, and me, I was helping with the coding of the models. And there is a okay, sorry, for some reason the presentation is having some issues. But I will go back. There was an embedded link there on the slide. Anyway, so when we did this in the class, we saw that students participated like scientists, right? So of course, this is not their regular classroom. They were taken to a computer lab and they worked on different computers, but the whole classroom dynamics changed. Students were participating like scientists, right? They were conducting experiments, they were talking about their findings, drawing graphs, showing what they saw, making their interpretations, and this is very different from what happens in a typical classroom. So these models have a potential for students to engage in their classrooms differently. Um, so this is an audio clip from a teacher talking about her experience uh, in a unit about uh, pendulum, so simple harmonic motion of a pendulum. And I request organizers to play the clip because there is some issue with the sound sharing.
Not vary the length and the mass in the lab, which they were able to do in that simulation, which they enjoyed.
Yes.
And they found out
Yeah, sorry.
that
Hello. Could you please pause? Could you please play from the beginning? I think it started in between.
good discussion and they will find their own inference and which I did not tell them. As we have planned this lesson with CT STEM, I have not taught that part they all first time in school. I wanted them to come out with their own findings and etc. And it was children who were discovering things instead of teachers telling them the direct path that here this is the formula or as such.
How was your role different as compared to other units that you typically teach?
Yes, like when I teach this chapter in work and energy, that kinetic energy, potential energy at the different points of the bob. I tell them that at the center there will be only kinetic energy, velocity is maximum, and some of them who are learning little slowly compared to the class, they even don't ask the question because they're scared of it. But here they did all this variation on their own, and out of these, I mean, below average students, many of them, they understood things on their own. So I enjoyed. So I think, which I already told you, I guess, that the content which is already existing in NetLogo is not exactly matching our CBSE syllabus till 10th standard. Those are very nice model to explore, but if I want to take it up as a day-to-day daily teaching, so I request you all to develop some content related to our syllabus, which I can use in daily teaching. So they all first time got an interactive surface where they have changed the variable, and after doing that they were trying to come to some inference on their own, and they enjoyed it. The good thing is that the same thing they did in their physics practical earlier. So there actually we had taken a bob which has a fixed mass and fixed length. So they did not vary the length and the mass in the lab, which they were able to do in that simulation, which they enjoyed. And they found out that the time period doesn't depend on the mass of the bob and everything. So they found all these things on their own. As they were working in a group, two children were sitting in one PC, so they had a good discussion, and then if some student was stuck, the another was coming up with their own inference. That way it worked very nicely for Yes, children. It was more useful compared to Educom, because here they will get into the proper line of scientific inquiry. They will find their own inference and etc., which I did not tell them. So as we have planned this lesson with CT STEM, I have not taught that part in school. I wanted them to come out with their own findings and etc. And it was children who were discovering things instead of teachers telling them the direct path that here this is the formula or as such.
How
Okay,
was
thank
your
you.
different
Could
as compared?
could you? Um, yeah, I think Philip got played the last part you heard first, and then first part you heard later. But that's okay as long as you heard her experiences, right? So there are three important aspects here: how students are learning, how we are designing these curricular materials, and what is it that we care about when we think about student learning, right? Sometimes we care about student getting good marks in exams, cracking their entrances, etc., etc., passing in the exam, or finishing the syllabus. But to be successful professionals in whatever domain that they choose, if they want to be doing cutting edge stuff, right, to become innovators, to become scientists, they need to be learning how to construct new knowledge, how to participate in these practices. And so these agent-based computational models allow them uh, to participate in this way in the classroom, so that they can be consumers of knowledge. Some concepts they don't know, their teachers is going to tell them, or their other students are going to tell them. They are going to be evaluators of the model, of the knowledge. So they are going to evaluate what each group is telling, and they could ask questions or disprove something that some other group is trying to prove, and construct knowledge, right? As a community, we uh, establish some claims that, okay, this is how the population is changing over time, or this is how temperature and pressure of the gas is related when we are studying kinematics, energy, and so on. So that how we are teaching specific topics uh, is very important, and these agent-based computational models can change that and allow students to become effective professionals in future. So there are three key takeaways from this talk. Um, it is important for students to be consumers, evaluators, and constructors of knowledge. Hashtag epistemically agentive learning. Agent-based computational models designed as ESMs can effectively support this kind of epistemically agentive learning, and involving teachers in co-designing such curricular materials is an effective approach to support students' epistemic agency. So hashtag co-design. Thank you so much. Thank you for being here. If you're there joining live, or if you're listening later, thank you for consuming the content. But I also request you to just go explore NetLogo and try it out. There are several models that are available. There are several units that are available on CT STEM website that I have created, but there are several other educators have also contributed there, and all over the world there are several platforms that use NetLogo models. So explore them, and you can also be uh, consumers, evaluators, and constructors of this knowledge. Thank you. I will stop sharing now.
Okay, so Dr. Sukat, let me start with some questions. Like in an undergraduate classrooms, how can this net logo models be used to teach specific concept? If you can just give us some overview about it.
Yes, absolutely. So depending on the topic, right? So NetLogo library has several models. And people have been using these models at undergraduate level. I have done this work only at the school level so far, but I think what is important is how these models are presented to students and how they engage with the model. So, for example, if you are teaching statistical mechanics, right, and a net logo model of a gas in a box can be very useful to teach some of the fundamentals idea of statistical mechanics, where students can do some experiments, collect data, have their hypotheses, and test them out, and maybe even modify the models to um, to learn more and even contribute to the community of NetLogo modelers. So, yeah, thank you for that question. Are there any other questions from the
So
audience?
how? Yes. So how can we use this approach in teacher training?
Okay, yeah, that is also an important question, because how we engage with teachers is extremely important when it comes to adopting any kind of new educational technology. And I believe that uh, involving teachers with their own agency is important. So a teacher should be able to say, okay, I want these kind of questions, or I don't want these kind of questions in my lesson, right? So if we are creating a lesson plan using a NetLogo model, what kind of questions should be there? Or even a teacher has a suggestion that, okay, let's change a model this way so that it's better to teach a concept, right? So if so the approach that I see in teacher training using these models is co-designing. So involving teachers as co-designers of lesson plans, curricular materials, or even models, depending on teachers' interests. So I have worked with a physics teacher, a school teacher, who was really interested in coding, and then we created a model and we modified a model, and she participated in the whole coding process because she was interested and she had some prior experience. So depending on teachers' interest, different teachers can involve in a different way. But I think from teachers' professional development point of view, our teacher training should involve teachers as co-designers.
Correct. So here, can you just tell us more details about learning about computational thinking with agent-based net logo models?
Yes, yes. So computational thinking is now becoming uh, a hot topic, and it has been defined in various different ways. So one way is sort of generic computational thinking, which is mostly related to computer science, and that involves, I mean, that comes from computer science, but it can be applied to all domains, like pattern recognition, etc. The work with NetLogo is about specific kind of computational thinking, and it's called computational thinking in science and mathematics. So the idea is that computational thinking differs in different domains. So artists use a lot of computational thinking when they're creating electronic uh, music, right? So if you're using computational tools to create music or create art forms, you're engaging in computational thinking, but that is different from how scientists engage in computational thinking. And the way scientists and mathematicians engage in computational thinking, they engage in four kind of practices that Weintraub and colleagues have identified. So, and which I had in my slides, but I will say them again. So, data practices, modeling and simulation practices, computational problem solving practices, and systems thinking practices. And those these are four sets of practices our scientists and mathematicians use in their work. So the computational thinking that can be supported using agent-based models, agent-based network models, is this, that when students are using these models, they're learning about modeling and simulation. When they're collecting data using these models, analyzing the data, etc., they're engaging in data practices. When they're debugging the code, they're modifying the code, they're engaging in computational problem solving practices. So I haven't talked about coding of these models, but the code is also written in a language. So NetLogo is also a language, and it's a platform, and it is designed to be easy to read. So you can just read a line of the code and you can understand it. Uh, so students can easily code in NetLogo. And systems thinking is also, since they're engaging with these emergent systems, they would develop learning of systems thinking. Thank you.
Yes, correct. So you talked about epistemic agency, right? So why is
Mhm.
epistemic agency important in a classroom?
Okay, that's a good question. The question on the screen was slightly different,
There is
but
there is one more question, so we can take it after this also.
afterward. Okay, okay,
No
great,
problem.
great. So yeah, first I'll talk about why epistemic agency is important, and uh, and that is because how we see our students in future, right? We want to see them as uh, people who would excel in their profession, who would do startups, be entrepreneurs, or be scientists, uh, be engineers, or whatever profession that they choose, they excel. And the excellence is sort of not following someone else, but to be a leader, right? And so that involves not just consuming knowledge, but being able to evaluate knowledge, what somebody else is saying, questioning that, and constructing knowledge, right? So when I'm talking about epistemic agency, I'm talking about consumption, evaluation, and construction of knowledge. Uh, and taking an active role in all these three. So, what kind of knowledge I want to consume, what kind of knowledge, how I want to evaluate that, and how I want to construct the knowledge. So, when we and I showed a set of practices, right? How if we teach those practices, then students can do all these three things effectively in future. So I think that is an important. That's why I think it's important to create opportunities for students to develop their epistemic agency.
Correct. So we have one question. Yeah, it's on the screen. During the discovery process of knowledge construction process, how can we check for alternate conception development in learners?
Okay, that's a good question. And so there are two things. One is, uh, in fact, when students are participating in inquiry-based learning or discovery-based learning of knowledge construction, um, they can develop conceptions that are not aligned with the established ideas in the field, which are referred as alternate conception, or the earlier word was misconception. So misconception is slightly problematic because how it was used in literature is problematic. The question here is asking, how can we check for alternate conception development? And so if a student has an alternate conception with an emergent systems microworld, with this kind of computational model, they can check that. And they would get a immediate feedback, right? Not a feedback from a teacher or from AI or something. They would get a feedback from their experiment. So they would conduct an experiment using this model, and if their conception is incorrect, then whatever they expect would not happen, right? And so they can test their ideas. So that is one big advantage of having these kind of computational models, but that requires validating the models beforehand. So the models need to be validated before they're used by students, but then the models themselves uh, can help students developing the more the canonical, more correct conceptions.
Correct. So now there are no more questions. So as we come to the end of this insightful masterclass, I wanted to express my heartfelt thanks to everyone for their participation and engagement. My sincere gratitude to Dr. Sugat for accepting our invite and for sharing your valuable insights and expertise with us. Thank you, Dr. Sugat. Successful conduct
Thank
of
you.
this event wouldn't have been possible without the strong support and guidance of our mentors, Sridhar Iyer sir, Briju sir, and Dr. Lakshmi Ganesh. Special mention to our technical team members, Dr. Yogendra Pal, Vivek Sabanwar, Nagesh Bokle, and Sandeep Yadav, and for their invaluable efforts. Thank you, everyone. And to our participants, thank you for your active engagement and thoughtful questions. Thank you once again for being a part of this masterclass. And we look forward to your participation in our future events too. So I wanted to make few announcements for the participants. You need to attempt the quiz and fill the feedback form, which will be available in your Ethics Society dashboard after you log in to your account to get the certificate for this masterclass. So thank you once again for being part of this enriching experience. Thank you, everyone. Have a great evening.